name is Maike and today I will be discussing the topic of logic, more specifically mathematical logic. In our everyday life, we communicate with sentences and statements. A sentence is an ordered collection of words that make sense. A statement is a sentence, but a statement can be either true or it can be false. This will be the basis of logic. Examples of statements can be the sky is blue and another statement is the sun is purple. Now for the first statement, this statement is clearly true and we can just write a T to indicate that. The second statement, the sun is purple, this is false, so we write an F to indicate that it is false. In logic, instead of writing each statement out every time, we can simply replace this with a single letter of the alphabet. Usually we write P and Q. You can use any letter that you want. These are called predicate variables. If we have again the statements the sky is blue and the sun is purple, we can negate these statements. Now this means we will get the opposite. So for the negation, we can indicate this with this sign or with this sign. So if we write not P, then we can say the sky is not blue. And where previously P was true, now the negation will be false. Now for Q, we can write not Q, the sun is not purple. And where previously it was false, now it is true. The conjunction of two statements can be indicated with the word and. So the conjunction of our two statements is the sky is blue and the sun is purple. We can indicate a conjunction with the sign or symbol, this. Now I like to remember it as an upside down bucket that traps two things under it. So both of them must be included. So we can write this conjunction in symbols as P and Q. For this example, this particular conjunction will be false because both must be included. So then we can say that both must be true for the whole conjunction to be true. So if we have a truth and a truth, then it will equal a truth. If either one of them is false, like we have here, we have a truth and a false, then the whole thing is false. We indicate a disjunction between two statements with the word or. The symbol for a disjunction is this. And I remember that if we have two objects and this comes between them, then you can choose either the one or the other. So we have our two statements here. The disjunction between them will be the sky is blue or the sun is purple. We can indicate this symbolically by P or Q. In this particular example, the disjunction P or Q will be true because P is true and Q is false. But we can choose either the one or the other one. So we can choose the P, which is true. So therefore it is true. A disjunction is only false when both of them is false. If both of them is true, then it is true. If only one of them is true, then it is also true. When we have two variables, P and Q, we can say that P can be true or false. The same goes for Q. Q can be true or false. Now, if we want to find the different combinations of true and false between P and Q, then we can say, okay, so P can be true and Q can be true. Or P can be true and Q can be false. Or P can be false and Q can be true. Or P can be false and Q can be false also. Now this is a bit messy. So the answer to organize all of this is truth tables. The truth table for two variables p and q will look as follows. So p will be true or false, and then we repeat true or false. Then q will be true and true, or false and false. So in this way, we have all the different combinations of true and false. So we have true, true, false, true, true, false, and false, false. If we have another variable r, we will have to double our truth table in size. So now where we have alternating true, false, true, false, true, false for p, and for q we doubled up. So we have true, true, false, false, true, true, false, false. Now for r we will double up again. So we have true, 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 and true, and then false, 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 and false. Out of this, we can clearly see that there is a pattern. So the amount of rows that your truth table will have will be 2 to the power of the amount of variables you have. In this case, we have 8 rows and 3 variables. So this rule holds because 2 to the power of 3 is 8. And then you will begin your truth table by alternating between true and false. And then you will double up and go to true, true, false, false. And then you will double up again, and so on and so on. Another important topic in logic is implications. An implication is an if-then statement. So an example is, if it is raining, then I have an umbrella. We can break this up into smaller statements. So it is raining can be statement P, and I have an umbrella can be statement Q. We can write this implication symbolically as P implies Q. An implication can be either true or it can be false. So if I tell you, if it is raining, then I have an umbrella. We can test if this is true for different scenarios. To do this, I have drawn a truth table. I have set it up just like any other truth table. You have P and Q, and here for Q we have true, false, and P true, true, false, false. So for the first scenario, a truth implying a truth. So it is raining and I have an umbrella. This means I told you the truth. So this is true. A truth implying a false. So it is indeed raining, but I do not have an umbrella. This means I lied to you. So this is false. A false implying a truth. So it is not raining, but I have an umbrella. This cannot be tested because it isn't raining. We can't determine if I will have an umbrella or not. So we say this is vacuously true. So this is true. A false implying a false. So it is not raining and I don't have an umbrella. So this means it is true. I did not lie to you. Another example of an implication is the following. If 2 plus 2 is equal to 5, then the earth is flat. So let's say 2 plus 2 is equal to 5 is P, and the earth is flat is Q. In symbols, this is in P implies Q. We know that 2 plus 2 is actually 4. So this means that P is false. This means we don't really have to go any further than this. It doesn't matter if P is true or false because we cannot test it because we started off with a false. This means that the implication is automatically vacuously true. So if 2 plus 2 is equal to 5, then the earth is flat because anything goes in this weird and wacky world. Here is an example of a general truth table. We have P and Q. We start by filling out Q's true values. We alternate between true and false. Then we double up for P. So it is true, true, false, and false. Then for the conjunction. Now remember, for a conjunction, it is only true if both of P and Q is true. So the conjunction of P and Q is only true for the first one because it's true and true. The rest of them is automatically false because they have at least one false within them. A disjunction is the less strict one. So here it is only false if both of them are false. So only the last one will be false. The rest of them will be true because at least one of them is true. Then the negation of P and Q is the opposite of P or Q. So not P is the opposite of P. So the true values will simply be opposite. So here we have true, so it will be false, and true will be false. False will be true, and false will be true again. The same goes for not Q. So because Q is true, it will be false here. It is false at Q, so not Q will be true, and so on. So here we have a false again, and then a truth. Implications work as follows. They are always true, except for when we have a truth implying a false. So here we have a truth implying a false, so this one is false. A truth implying a truth will be true. A false implying a truth or a false implying a false will automatically be true because it is vacuously true. In the next part of this video, we will look at a few important terms. Then you will be ready to tackle any logic questions that get thrown your way. Firstly, we will look at biconditional statements. This will be indicated in a test by the words if and only if, or it can be abbreviated as IFF. The symbol for the biconditional statement is this double implication symbol. Now, it is exactly that. It is a double implication. So the biconditional of P and Q is logically equivalent to P implies Q and Q implies P. So this is only true if the implication P implies Q is true and if Q implies P is true. Next, we will look at the converse and the inverse of an implication. If we have the implication P and Q, then the converse will simply be Q implies P. You just switch them around. The inverse of P implies Q will be not P implies not Q. You keep it exactly the same as this implication, you just negate P and Q. Note that this inverse of P and Q is not the same as P and Q, nor is the converse the same. So these are not logically equivalent to each other. The contrapositive can be obtained by getting the converse first, and then you get the inverse of an implication. So if we have P imply Q, the converse will be Q implies P. And then we get the inverse, and that will be not Q implies not P. So this will be the contrapositive. And note, this is logically equivalent to the implication P implies Q. The next thing we will look at is tautologies and contradictions. Now, a tautology is something that is always true. It doesn't matter what the values involved are. An example of a tautology will be P or not P. Now, if P is true, then not P must be false, or vice versa. And because at least one of them is true, this means that the whole thing will be true. A contradiction is something that is always false. An example of a contradiction is P and not P. So again, we have one true and one false. And because at least one of them is false, this means the whole thing will be false. For the last part of this video, we will look at logical equivalence. Logical equivalence is indicated by this symbol. Logical equivalence is when two things look different, but they mean exactly the same thing. The sign for logical equivalence is this equivalent sign. We can think about this equivalent sign as the equal sign of logic. With logical equivalence, we have certain laws that apply. The first one is the commutative law. Now, this law says that the order isn't important. So if we have P or Q, then that is the same as Q or P. You can switch them around. And the same holds for AND. So P and Q is the same as Q and P. The second law is the associative law. Now, this law states that brackets can move. If you have more than two variables, you can group them together and the meaning of the whole statement will stay the same. So for example, here we have P or, and then in brackets, Q or R. And that is logically equivalent to, in brackets, P or Q or R. And it is exactly the same for AND. But the symbols must be the same. So you must have all disjunctions or all conjunctions. Otherwise, it will not be true. You can't have both. The next law is the distributive law. Before we look at the distributive law, let's first do some revision about multiplying brackets. So if you have A times B minus C, then you multiply the A with the B to get AB, and then you multiply the A with the minus C to get minus AC. The distributive law works exactly the same. Let's look at P or, and in bracket Q and R. So we can multiply, although it's not really multiplying, the P with the Q, and then we have the P or Q. And then we can have the P or the R. And in the middle, we have to connect them. And this will be what is in the bracket, the symbol in the bracket. So this OR will be multiplied in with the Q and the R. So it will appear twice, while the AND will only appear once. And then we can do exactly the same for P and in brackets Q or R. So here we will have the P going to the Q, but with the AND. So then we have P and Q, and then we have the same for P and R. Then we have P and R, and then the sign in the bracket, or rather the symbol in the brackets, will be connecting the two new brackets. The last law is the Morgan's law. The Morgan's law is used for negations. So if we look at the example of not P or Q, then this will be logically equivalent to not P and not Q, because we have multiplied, in a sense, the negation of the P to get not P, and the negation of the Q to get not Q, and also the negation with the disjunction to get the conjunction, because the disjunction and the conjunction are opposites. Then we can do exactly the same for the negation of P and Q. So the negation with the P will become not P, the negation with the Q will become not Q, and the negation of your conjunction will be your disjunction. So it is as easy as that. This brings us to the end of the video. Thank you so much for watching, and I hope this helped you to understand the basics of logic. Till next time! It is possible that the Earth is flat, yes. Look at it. Yeah. The contrapositive of P implies Q. Never.